we're going to speak about clustering. It is an approach inside of unsupervised learning, because in unsupervised learning, as Beatriz will explain, we also have dimensional reduction that we have in last session with Yeshena. So these techniques that we were talking about, it is also in unsupervised learning. Okay?
So, good evening, everybody. I'm Beatriz. I'm a researcher here. I did my PhD in unsupervised learning with focus on clustering. Basically, in my PhD, I combine machine learning, clustering, with some optimization strategies. It's a new approach. Today, I will present like an introduction about unsupervised learning, focus in clustering algorithms. This is the contents of the course today. First, we talk about clustering unsupervised methods. What is the difference between supervised and unsupervised? I hope you have previous class about machine learning and supervised methods. Now I have a different approach. After we talk about some methods and some specific algorithms, the most well-known algorithms in the literature, the most well-known and used in data analysis, that is k-means, hierarchical clustering, DB-scan, and clustering based on models. In this context, we have the Gaussian models that are the most used. After some methods of validate if the clustering algorithm, the cluster method and results is good enough for your application, and some practical activities in the last part of the class. So, unsupervised learning. There are different approaches to classify supervised and unsupervised methods. Some authors categorize in a way, others in a little bit different as this one. This approach that divides supervised, unsupervised, and reinforced methods is the one that I most agree compared to the other. You can ask questions at the same. Please don't wait till I finish all the presentation. Ask questions. Please interrupt me and ask anything. You can ask, for example, and methods based on neural network deep learning. Where is this method in this context? For me and for the authors that categorize as this way, we considering neural networks, deep learning, a different kind of learning. It's not specific to machine learning. It's not specific to machine learning. Okay. In supervised learning, normally we have a vector of in the output. We have some to compare the input vector with the output vector. We have the information previous about what we are categorizing. On the other hand, in unsupervised learning, we don't have the output vector. So we have an information to provide for the algorithms, and in the end, we don't have a comparison. For this reason, unsupervised methods is more difficult to automate to make the algorithms completely automatic. Because in this case, we needed the presence of the decision maker. The decision maker, in the end, needs to take the decision of what is the most appropriate solution for its problems. And reinforcement methods is normally used in more industrial contexts. It's another kind of algorithm for used in robotics, for example. And for data analysis, normally we focus on supervised, unsupervised, and the other category that is neural and deep learning approaches. Here we have the same divisions as supervised, unsupervised, and reinforced methods. In supervised, we normally have classification and regression. In classification, we classify a data set in if, for example, we have a data set that contains fruit. We have apples, bananas, and so on. We provide some information about this fruit, for example, pollen. Some of them is red, the other is yellow, the other is green, and so on. Information about the size, if it's brown, if it's not. And in the end, we have a comparison of the input vector and the output vector. We classify these elements and compare in the end. In regression, we make a provision about what is happening. For example, forecast. We have the information of the previous day, and we have information of today, and we need to provide what is the temperature for tomorrow. In this kind, we use regression. It's one example. And in unsupervised learning, as I said last week, we had a class of last week? Reduction. That is the other class of unsupervised. And today we have clustering. The box, inside the red one is the most well-known algorithms of each class. For example, in terms of clustering, k-means is the most famous of the literature, for example. We have others that use some specific contexts, but normally k-means is the first option because it's easier is the easiest to be codified, and it have in all languages, Python, MATLAB, and so on. But it's not so robust for real case study. It's worked very well in rounded data. If we plot a scatter plot of a data set, and the context is we have some groups rounded, that means we work very well. But if it's not a core, it's a mix of geometries inside this data set, probably k-means will not work. It provides an error and the solution do not make sense. We have others algorithms most specific for the situation. So clustering consists of grouping the elements according to its characteristics. Basically, for example, in this figure, we have an initial one that's every circle is black. We have 3 categories. Sometimes we know how many categories we have in the data set, other times we don't have information. But in this case, we have 3. And after applying the clustering algorithms, these elements will be categorized in different groups. One green, the other red, and the other blue. There are different ways, different algorithms to do this categorization. Most of these algorithms are uni-objective. What does it mean? There are only one function, one parameter that defines the function. In my PhD, I developed a multi-objective clustering. That is another approach. In this case, I consider more than one function to categorize the data. It's useful for complex situations, real case situations that we have a lot of information, a lot of parameters, and normally the only objective algorithm is not enough to work with these complexity. So we use another kind of algorithms. There are basically 5 types of clustering algorithms. I talked one by one with presenting the characteristics of each one. The first is the partitioning. Basically, as the name says, partitioning means partitioning the data set in several subsets. And in the end, we compare if this subset is similar to this one, we can join or you can partition in others data set. Partitioning is the class that Camille is part of, and it's normally most appropriated for rounded clustering, but it cannot, most of the time, it cannot work with complex, it tends to produce only complex clustering that's related with the geometry. And it's difficult to work with nominal or ordinal attributes, so only with numeric values. And one of the most talked characteristics of this class is it's required the previous information of the number of clusters that we have in the data set. So if I'm categorizing, for example, foods, I need to know how many classes of that foods we have. If we have 5, 3, or 2. For instance, and we can know if we have more or not. But considering a data set with fewer information, it's really complicated to provide this information for the algorithm. So we have some strategies to provide this, to try to define the number of clusters. But we have other things that do not require parameterization. One example that not require the indication of the clusterings is the hierarchical method. Hierarchical basically is, you know, the tree of in statistics that subdivides the, basically is this approach. It's partition the data set in hierarchical categories, and according to the number of clustering, the final answer is defined. We have more specific examples in the end. We can talk more about more practically in terms of the algorithms. Density-based is algorithms based on the density of the data, where the data is located. If you have a concentration of data in this part, we have a cluster here. If you have another concentration in this part, we have another cluster here, because this part is not unique. So if you have something here, another here, and another in this part of the space, we have 3 clusters. Density-based clusters is very appropriated in data sets that we have outliers, because the previous one and sometimes the last 2 is not able to recognize outliers in clustering algorithms. It's just categorized as one of the categories. But density-based clusters are able to say, oh, this data is an outlier, it's not part of the cluster. I don't know if you have a processing class. Do you have any class about outliers? No. Okay. Just to clarify, when you have a data set, sometimes some elements of this data set is not exactly, it's considered a noise. So it must be removed from the data set in some cases. In others, we need to work with it. So it's hoped that the algorithms can identify which is an outlier and which data is not an outlier. Sometimes it's possible, other times not possible. In this case, the data cluster can define what kind of data is an outlier, not, and the others, it's harder to really work with. The grid-based, basically it's define the space of search in a grid and define the clusters inside the grid. Basically, this is another kind of approach to divide itself, and is really worked in higher dimensional data set. When we are working in R5, 6, 5 dimensions, 6 dimensions, it's really appropriated for this case. But normally, we have 2 or 3 dimensions. Normally, in all data sets we have this. In real case, we have a little bit more, but depends on the case. The grid it's appropriate. Other times, it's better to use a multi-object algorithm. And the model-based is like what is your creative able to do it. It's based on the model, like a Gaussian mixture is based on the Gaussian distribution, the Gaussian probability. And it's another completely different that depends on the function that is being used inside the algorithms. So we have a lot of examples of model, but it's really specific for depends on the situation. If the data set have one specific distribution of the data, probably if you use the same distribution in the clustering model, you provide the results. So here we have a lot of examples of clustering models. The big question is which use, in which moment, which data set, and the answer is, I don't know. Which algorithm used in which moment depends on the data set, depends on the problem that you have. For example, if I have a data set that's rounded, it's not necessary to use a complex algorithms. We can use a k-means. But if you have some data that is very joined in the space, it's most appropriate to use, for example, an algorithm based on densities. Scan, for example, depends on the problem. In data analysis, in supervisor, any kind of problems, all the answer will depend on the data that you have. And it's really complex. It's not easy, do not exist an algorithm that will work very well for every situation. We have a theory that proves that the answer depends on the data that you have. If you have, for example, here 30, 20 people, if everybody have a different problem, one algorithm will be completely different for each problem. So depends on the data. Depends. That's the reason. Depends also the knowledge of who are using the algorithm. Sometimes we have algorithms with completely different answers, and the decision maker that is codifying needs to decide what is the best solution. So it depends on its knowledge about what is happening inside it. Now with LLMs, ChatGPT is really easy, put the data there, and give me the answer of this considering 3 clusters. It's easy, but why? That's the importance of understand what is happening inside the algorithm, what is the context that each algorithm is created for each case.
Can I stop just to do some graphs because I like this. So imagine all of us are more or less aware of what we are talking about when we talk about unsupervised learning. Means that the data is not identified. I don't know what is data. Okay. So, for example, if I have the age and the country of each of them, we are all spread, and I have to analyze what kind of things and how I can do this you. Okay? Sometimes it's super easy because when we have something like that, we know that we have to group, and there is no problem. So I know that when I see the data, we have 2 groups. Can be, for example, that in each group I want to divide it. And we have, for example, this kind of cases. But imagine, for example, that we have your analysis. Okay? And I want to personalize if you have so I really don't know where, and this is the problem that we have in unsupervised because I don't know for each one what each if they have disease. So we need to group, but we don't know nothing about one kind of information it is, okay? So we need to use all methods because when you say, okay, give me just one, it is impossible, okay? Because you will see in the hands-on that when you put one method gives information, when you put another information, and it is still that you need to say. What is more interesting for your goal? If I want to quantify the result of this, I put if I want to quantify the result of how I create the funding, I should say. So it is your information as a decision, as Beatriz was saying, that it is important to know. I should select this information or I should select this one. Okay? Yeah, of course.
There's another thing about using all. Sometimes you don't know what you need.
Exactly.
Sometimes you don't. Oh, if we do this, there is this clustering, and that explains this thing that we were worried. What is this? How would this explain? Because there is a connection, partition. That's why you try, not only. And in the end, you'll see if you are satisfied.
Exactly.
Yeah.
So here that is to extract information from the data, but how we should connect. And this is the problem, okay? Because if I have, this person has disease A, this person has disease B, this person has disease A, I don't need first because it is available, I agree. But if I want to try to understand what are the main features, what can be connected when I have a disease A, this is what we use to into classroom. Porque eu preciso explicar entre essas.
And for example, in unobjective clustering, we only have one answer. Yeah. In multi-objective, we have 7, 10, 100 answers. And the decision maker, after running algorithm, must select just one. So the knowledge of the decision maker is really important in unsupervised learning. That is the reason that it's really complicated to create an algorithm completely automatic, because the decision in the end needs a human knowledge. So it's a completely different situation compared to supervised learning. So now let me check. Okay, measures, increments. We talk more about each class of clustering, starting with partitioning that others said that we have in the second case, in the second group, we can partition it in another subset. And the challenging clustering partition is define this position. The algorithms, for example, K-means, record this number. If you have this data set, just look, we can classify on cluster 1, cluster 2. But we can also have the cluster 3. For any kind of reason, we have another cluster here. So, K-means, for example, require this information, how many clusters there are in the data set. And depends on the knowledge of the decision maker. Again, the decision maker is really important in this case. Can you pass for the next? And partitioning. If we are partitioning something, we need to establish some measures. There are a lot of measures. So what we have here, a lot of algorithms, a lot of measures, a lot of results. It's very difficult to define. Sorry. It's very difficult to define what is most appropriate for all data sets. So we don't have an algorithm that will be excellent for all cases. And we can change a lot of parameterization. For example, we can establish a measure between the centroid and the data as an Euclidean distance. But we can also use another kind of measure, for example, cherry, like this distance. And these results, these measures, we change completely the results. So we need to define what is the most appropriate. Normally, we use Euclidean distance for all cases. It's the most used, the most appropriated in most of the cases, but sometimes not work so well. So we have another possibility. This 4 is the most well in the literature. And we use these measures, one per time, to define the clustering distance. There are a lot of ways to measure clustering distance. This, the 4 first, is the most used in the literature, but you can play with this distance in using combine each one and define other kinds of measures, other kind of algorithms. I did this in my PhD, and during 3 years, I'm playing with this equation and change some parameterization to find a different solution of a complex problem. So, for example, I can use, as we're talking about unique objective, we need to define just one measure to use during all the process. And normally, we want to minimize this measure or sometimes maximize or define a relation between. So, considering this case, imagine that we want to maximize the distance between the centroids. So I'm talking about Euclidean distance, about this sum, 1, 2, 3, the sum of the 3 distance. This is the centroid distance. And the objective of an algorithm that uses this kind of distance is maximize this one. Imagine in the first interaction of the algorithm, we have these results. And in the second interaction, we have another solution, another centroid, like this one. You have, sorry, but this is a line.
It can be Euclidean if you put correctly the also around the.
Yeah. So it's a line. It's a line. Yeah. In the second interaction, we have this position of the centroid. So clearly the distance between the sum in red and the sum in blue is highest than the first one. So if you have the centroid in this position, we maximize the distance. And the solution in blue is most appropriated for this case, for example. But we are talking about just 3 clusters with few elements. And in the end, if you have this as the ultimate solution, it means, for example, normally adjust the position of the centroid for the bicenter of the data set, the geometric center of the data distribution. And it's try to adapt for a position dependent. A little bit depends on the element. But this is an example of centroid distance. Ish. Single linkage is the distance between the element that belongs to one cluster to the element, the nearest neighbor of another cluster. Complete link is the opposite, is the furthest neighbor between different elements that belong to different clusters. Average is the average of the distance between the elements. And watered methods, it's the square distance between 2 different clusters. It's another approach. But we have much more than this. For example, in my PhD, I compare 42 situations, and here only have 5. We can combine this in uni and multi-objective in infinitive ways. It's possible. And all difference between the metrics or the distance will provide a different solution. So the decision is again responsible. It's a responsibility of the decision maker in the end. So the knowledge about what happened inside algorithms, what happened in the data set, is really important in unsupervised learning. So K-means, for all examples.
No, I'm happy.
Okay. Okay. For all algorithms that we presented today, not this one, I left some videos. You can use this video is really the way that you present how the algorithm works. Because just present the pseudocode here is not interesting for you. And in this case of the videos, we have an illustration. Basically, so in K-means, the first line is kappa, key, the number of centroids. We need to know. Looking for this case, we know that key is equal to 3. After, we need the final measure to evaluate the distance in this situation. Normally, the K-means uses the SSE. E measure. That is the distance between each element to the centroid. And we need to minimize this distance. So the final solution is the minimal distance between the centroid, define the position of the centroid in relation to each element that belongs to each cluster. So the algorithm will change. Basically, the position of the data is fixed, and the position of the centroid is changed throughout the process. So sometimes it's here, other times here. And in the end, normally, in the K-means that we are talking about around the cluster, normally is the one in the center of the data set. Basically, this is K-means.
But there are several versions of K-means. So we already saw K-means like that, but sometimes use other. So it is important to use to know what kind of measure it is. And do not be surprised if you use, for example, K-means of Markov K-means of Python.
Yeah, we have this problem. Depends on the language that you codify. We have, if you have the same algorithm, the same parameterization, the language of the code can change a little bit in this case. Yes.
What does iteration mean?
Iteration.
Iteration.
Lift. Ah! Lift. Lift, okay. Okay, the D. Here's the D.
It's the distance. In this case, it's a radius of the distance. The lift, it's a different kind of measure that was used in this pseudocode. It's just this.
It is the difference between the centroid and the points that are inside of it. Okay, so this is the context.
So the second algorithm is the Gaussian mixer model. This is a specific kind and completely different from the others algorithms that I will present today. Normally, in clustering, we have in this case, and the next one, we don't have a signature. It's one of the difference. But the main difference between the Gaussian and the other methods is, in this case, we have levels that the elements belong to each cluster. For example, here in the figure, the elements closer to this center, that is not a centroid, it's have a higher probability to belong to this clustering, and the lower probability to belong to this one. This kind of approach is named as soft clustering. Another example of clustering that has a similar approach is fuzzy clustering. That is another different way. But the difference between this one and fuzzy, here we have probability, and we can name it and talk about probability of belong to this cluster, or for example, 40% and the other 60%. And in clustering algorithm, we cannot talk about probability and this in this way. This is more closer for our perception than clustering approach. This kind of algorithms is most recommended in situations that we have the data overlapping. Because, for example, these elements here are overlapping in the area of the blue cluster and the red cluster. So we have a kind of fuzzy and insertance inside the data set. So we cannot, it's really difficult to categorize this kind of element in one specific cluster that is a hard cluster. Normally we call hard clustering when we have just one classification. And when we have more than one is software clustering techniques. Hierarchy. We also have a video here. In this case, we built a binary tree. Normally it's binary, but could be with more subdivisions. And imagine that all data is in the beginning in this part of the tree. So in the beginning, we have this data that are in the top of the tree. If you divide like this, we have two groups, which means two divisions. So each divisions means one branch of the tree. And here we can have, for example, like this. We have a subdivision of this group that was initially like this. And if we divide it here, we have another subdivision. And if you divide this, we have another subdivision. That this part is here, and this part goes to that point. And so on until in the end we have with the final classification. The question here is how much cluster we have in the data set. For this, We have a lot. We have a lot of data. All data is categorized here in the end, but we have a lot of possibilities. Again, the decision maker must take a decision. So how the decision is taken in this case? We have this line that is related to the distance between the clusters. And for example, if you have a cut line here in this position, we have 1, 2, 3, 4 clusters. But if it goes down, so if the line and this one in black, we have 1, 2, 3, 4, 5, 6 clusters, and here 1, 2, 3, 4, 5, 6, 7, 8 clusters. So depends on this variation. In this case, the decision maker must consider the distance among the data. If these lines goes down, means we have more subdivisions and the data is closed, is more homogeneous. And if the lines go up, the data is not so well divided, but it's not mean that it's wrong. It's mean that the data inside each cluster is not so equal. For example, if the line is here, we have normally all the elements very close to each other. The characteristic is very close to each other. And here we have more difference between the data that are inside each cluster.
Yeah. And interesting thing is that in the worst of situation, in the worst, I can always cut here, right? And if I cut here, I have 2 clusters because it is the minimum number of clusters because we cannot have 1, right? 1 is all the same. So the minimum always is 2 clusters, 3 clusters, 4 clusters, and so on and so on. And you should cut in order that all the boxes are more or less equal. Never will be totally equal, but homogeneous.
In this case specific, this cluster is provided by a data set that categorizes the answers provided by a set of students in a test. So I think it's the probability of correct answer here. So this group here have a similar performance to the test that is completely different for these one, for example. And if you cut here, we have we have 4 different groups of students. One will do very well in the test. The others have a poor performance. The others in the average. But if you have inside the cluster, inside this 4 cluster, I cannot extract some information. I want more information about this. I can subdivide it, for example, this one in a multi-cluster. And we can, in some situations, have more information with these subdivisions. And this is the last one that is completely different for the others. DBSCAN is the density-based spatial clustering applications with noise. Noise in this case is related with outliers. So I use the same. Imagine that we have this, and we also have this data in this. So what I mean with outliers is exactly this one. For any reason, sometimes when the machine or the algorithms or the person are collecting the data, or we have a specific situation, these things won't work. That is, it's called outliers. So the information of these elements diverge completely from the whole data set. It's normal in data maybe without because it's really complicated to categorize. It's more complicated work with data related with health than data with machine. Normally in data collected by machines in industry, we have a situation like this one. But for example, considering pressure, blood pressure, for a reason, when people have a completely different one, considering the same, a group of people the same age, the same gender, the same work, very specific. And one of these people have a higher pressure for, I don't know why, but the data is completely different. In this case, we have outliers. And in situations like that, this algorithm is very recommended because it is one of the algorithms that able to recognize this kind of data and say, oh, this is not part of data, this is an outlier. If you use k-means, in this case, what k-means will do is years cluster, for example. It's trying to adapt the answer to the data set, and it's not correct. So what happened here is there are two parameters. That is the mean points and the epsilon. The mean points, it's a minimum number of elements that belong to a cluster. So let's consider 3. We have and the epsilon is a distance. Let's consider just one. The DB scan started with a random point, like here. And if epsilon is equal 1, we establish a radius 1, and we try to group this as one cluster. But the mean points in this case is 3, and here it won't have 2. So this solution is not feasible. What the algorithm will do? Select another point. Restart. And if it's also 1, it's equal to the roots. In this case, we have 5 elements inside this region. So satisfy this condition, and we start with this. What is the next step? It's move, go, and down. And we also, in some situations, have more than one regions. And for example, here we have another cluster. And it's try to expand this for the border regions and join the next the elements that are next to the regions to have the all the elements classified. In this case, that I'm not present there, we started, for example, in this point here, and here we have a clustering that joined with this one, and here we have one clustering. This region have a higher distance between this cluster and this one, so it's not joined. Here we have another cluster. And for example, the points that are in this position and in black, not in the green and blue regions, is the outliers. Because with a specific parameterization, I don't know, mean points in this case 7 and epsilon is 1, these elements never satisfied these conditions inside this box of the algorithms. So it's a completely different approach. It's very interesting when we have outliers.
The epsilon would be what is the distance, right? But in the first case, not possible because it's only two. For example, it's feasible to make the decimal or like how can I say, how can I have sure that my decimal is required not testing? Okay.
Key point in it is always
Okay.
and you need to know.
Okay.
And of course, when you have more information about it, and when you explore, this is really patient action, okay? So you explore and you need to discover things and be to increase and then so this is not so that's good. That's all. So it is not a very defined, just some feelings, and this is the most question is
Just, always, we cannot use the same epsilon if the problems are. And therefore, again, is the surgeon that knows, okay, I'm dealing with the health, and I want the parameters be with those, they are on the same side, right? And this idea is to eliminate all the noise given by the. So if you put a big epsilon, they don't see you.
and you have to answer that.
Yeah, and it's possible, depends on the parameterization that we have. In the end, we have just one cluster. The algorithms give this answer for us. That's incorrect. And we need the knowledge about what happened inside the algorithms, what is the process to define, okay, this is not a correct answer. But the algorithms I don't know if k-mean sometimes give an error message in MATLAB, but in Python, I think it's give the answer just one cluster. Also, dbScan gives one cluster as a possible solution, but we need to know that it's not possible in real case.
And in real situations, what happens usually is that, okay, we have a proposal. Us as researchers, we have like I think that is better and already have a lot of this kind of thing. We think that it should be part in three clusters, distributed like that, with method with math. And we go to the paper. And we say, okay. So what we find is that this kind of and usually always majority of the time with it not the case. Because this kind of information will be charged. We go again to the law. And this is really an interaction between the owner of the data and also the researcher. So we need to be always be very close communication. But sometimes if we divide, we found this kind of visualization. And that makes sense now that you say. And it is like that we discover these insights of the inside of the so it is really, it's not a basic thing. Sometimes we talk that we are like investigation, not research, investigation inside a we always like let's check with police question and case method. So get another result. It's like a private thing, you know. We need to discover, oh, this is the thing, and try to join the thing. For example, here, how many questions have we have enough.
The clusters, we also need to know the axis.
You need to understand it. You need to know it. Feeling.
And for example, this example is only objective. In the end, we have one answer. In multi-objective, in the end, we have, for example, 10 possible answers. The number of cluster key can vary 2 to 11. Can you repeat? Okay. 2 to 7. Which means that with one algorithm, we have 10 possibilities that varies between 2 to 7 divisions, and the others, of course, we don't have. We have different position of the elements. One algorithm says, oh, we have 2 clusters. Okay, the divisions here. The other says, the other correctly says we have 2 clusters. Yeah, but the division is this here. Cluster 1, cluster 2. So we need normally a previous knowledge of the data. It's all related with data, as you said. And the information that, for example, in industry or if you work in a hospital, the previous information of the specialist, doctor, and engineer will define and will support us as decision maker to give the correct information, to define the correct, the final answer as the most appropriate one. And for example, if you have these 2 divisions, and you are talking, as Anna said at the beginning, we are in a hospital, and the doctor says, oh, we have these patients. We know that we have 2 kinds of disease. And if I give a return and say, oh, we have 2 types of disease.
So we know the number of facilities.
Yeah, we know that we have, and which more? I don't know which more. So if we as decision maker return professional with the same answer that we have, so in this case, we know that we have 2 clusters, but inside each clusters, we can subdivide. For example, this cluster, this one, and this one. We have 2 types of disease. This one is in advanced stage of the disease. The same disease has this patient, but in another stage. This one is not hard. It's not. And in the case of this disease, we have 4 different stages, and which means that we have the doctor must provide different kind of treatment for these 4 patients, for this 2, and so on. So we know in the beginning that we have 2 diseases. Here we have 2 diseases, but we have a little bit more information that can define the treatment, define if the patient will alive or not. Yes. And here we have accounts. Because we have 1, 2, 3, 4, 5, 6 data sets. Each line is 1 data set. And we have 1, 2, 3, 4, 5, 2, 3, 4, 5, 6, 7, 8, 9, 10 algorithms. The algorithms in the first line. For example, DBScan can recognize in the first case that we have 2 clusters. But the first 3, in this case, we have 2 clusters, but a completely different situation as this one. In this case, we have 4 clustering, 3 clustering, 2 clustering, 2 clustering again, but in a different kind of distribution, and so on. This one is used as a benchmark data set that's used to test if the algorithm works. When we are developing a new algorithm, we use this kind of data set to test, because this solution is very well known in the literature, and we know what is expected for the algorithms. And this is, if you look for this data, it's clear we have 2 clusters, but for the algorithm categorize this kind of geometry, it's really complicated. And DBScan can work very well in this case. but the others have completely different classification. And in this case here, we have a lot of outliers, as I mentioned before. And these algorithms here cannot recognize outliers. So it's join the noise of the data as a real data and provide the wrong information for the decision maker. Similar for this line here. In this case, we have a simple one because we have rounded data and space in a different position of the space. So all the algorithms provide the same distribution. I know the color is different, but
It is same.
it's the same distribution. We have three.
Color.
Now, in that line, I think that is, I don't know if it is clear, but in this line, this solution is just one. Okay, just depend of the color, but the color is randomly. Okay, but here it is clear that we have 3 clusters and all of them gives 3 clusters. So what we want to know is, don't forget, the color is just to illustrate. But the important thing here is that different, and this is what we want to share with you. Different algorithms can give different information. It is you that should select the information and what is better for your specific case, and what is the measure you can test and try to do some experience until you are happy with the answer. Okay, so it is really like that we do in cluster.
In the last line, we have again a different solution. This one is really curious because the algorithms categorize the whole data set in blue. And this one for one specific case that I don't know, it's categorizing different clustering. It's not make sense here that the solution it's provided, but it's not feasible for the problems. The decision maker must know that it's not
Except if you want to outline,
yeah.
things that this is not a feasible.
And this one categorize just one cluster. As I said, sometimes some algorithms can provide this information. We only have one clustering because it's like a bug in the data set, in the codification. Normally, when we create a new algorithm, we establish that the minimum number of clusters is 2. But in some cases, it's not guaranteed. Sometimes the programmer forgets this part.
It is not a mathematician.
Yeah. And
This thing to always measure.
Yeah.
You have different measures. Show. And these measures influence totally the way you consider data proxy.
Similarly.
Similar. And sometimes the measures that you use regarding the data you have that it is related to a specific problem don't make sense.
Yeah.
And that's like you cannot like use Minkowski distance in this case because it doesn't make sense.
No, when we are talking dimensions, we are not
Yeah, for example. Just an example. Yeah.
Take notes. This is for 50 minutes. Yeah, we need to.
So this is what you should have some measures. This example that Minkowski means or like that or others, but the point is that sometimes the algorithm is okay, but the point is at some point in the algorithm you use some measures that for that specific data is not reliable. That is why it happens. It's things.
And that is when we don't like imagine you have a company and they say, okay, give me a size of our company. So when it is like that, we never come. Okay, and that is the reason that we need, and this is what we really want to share. We never should use just one algorithm to find the data. So we should, if you really want a good job, you should try to explore the maximum algorithms with the maximum of information, try to use the information that you have and have this iterative situation to go to the owner of the data, give answers, go to owner of the data, give answers, in terms to fit the best situation. And sometimes it's init, sometimes it's a scan, sometimes it's either stage, either tree. Yeah. Hierarchical trusting and so on. Okay, so this we don't have, and good thing because what means that we have. Okay, so we don't have a very deterministic way to do the person. What is makes sense? Okay, researchable. Okay.
But when we have two dimensions only, we can use our eyes.
Yes, of course. But sometimes our eyes can be. Okay. Because sometimes what you see when you analyze the data, you can extract more information. But of course, in this case, our eyes say this is frequency. Right? 2 dimensions, 2 clusters. But for example, here it is not clear. We have some situations of problems that can be like that, but can be as a wrong, like this one. Okay, this can be right and this can be right. Depend of the problem. Depend of what representing that. So it's not clear. That is.
For example, this one is segmented, but I can see 4, 3, 7, 10. We looked for the data, but the eyes are seeing, but we're not categorized.
Yeah, about the data. And usually, but we will do a small exercise about that.
I think it used to be the last one, first one, because you can see like 10 clusters different with big one.
And sometimes we do like that. So sometimes having much clusters is better than have just small clusters. So we can, for example, in this kind of data, we have 3, so we say add 3, and we give this solution to the owner of the data, and he say, okay, makes sense to have this division, or do not make sense, and should be just 1. So stay like that. Okay.
So one of the way that you can use to define if the solution is good or not, it's appropriate or not, is using the validity index. The problem here is we have a lot of them. Which one we need to use in this case? Depends on the data, depends on the situation. Here we have 30 examples. And after you present the elbow and the silhouette index, the objective here, each one can also use it as a measure in the algorithms. Sometimes we want to minimize the measure, other times we want to maximize. And we can also use the solution provided by the algorithms and compare with the solutions provided by this measure. If we have a match, probably with the solution of the algorithms, it's okay to use it. But these tools, the CVIs, is normally used when we don't have any information about the data. We don't know if the answer is correct or not. So we use these tools to have more information and to compare if the algorithm is developed, it's appropriated, it works in benchmark situation or not. The two most used in this case is the elbow method. Basically, we have the WSS error, this annotation that I forgot to put, sorry, but it's easier to find it. It's compare the distance between the elements and the centroid. And here we have the possible number of clustering. If you varies the number of clusters, we have a different value of WSS. And looking for this graph, we're trying to identify in which point we have an elbow in for mathematic, the change of the equation. In this case, this point here is the most appropriate one, and probably in the data set 4 is the number of clustering. Another way to analyze this,
But once again, not in a deterministic way, so it is just a proposal.
is define the line between the first and the next and the last number of clustering, and evaluate the maximum, the distance between the point and the line, and the maximum one, because elbow is a maximization measure. The maximum one is the recommended, but it's a recommended, it's not the true, it's not the, we can have other situations. And the other that's very used is the silhouette. And for example, here we have a different solution. In the first, we have two clusters with
Two.
Two clusters.
Two clusters. In the second, we have 4 clusters, and here six clusters. It's the same data set. It's the same algorithms with different parameterization, and we have 3 different solutions. We can have much more. So depends on previous information that we have about this data set. In this case, we have the eye to visualize in 2 dimensions. Maybe here we can consider 1 cluster in there, the second one. But for me, this one is the most appropriate.
Yeah, because the bars of the silhouette are more near, okay? Instead of the others that in the first one, the second bar is too big, and in the sixth one is too long, and the other one is too short. So the more equilibrium bars, yeah.